job, man. Forgot to remind me.
Come on, Redmond.
Redmond.
Come on,
Redmond. You remind me.
I didn't look at my phone, sorry.
Redmond. So remember we had this kind of this picture we were drawing where we're in our minds we're shooting this bullet straight up off of right by the edge of El Capitan, that big face of El Capitan, and we're shooting it up in the air, and the bullet's going to go up to its apex, come falling back down, and just fall right by the side of the cliff. Okay. The bullet, remember, is coated with sliprium, so it experiences no air resistance. Okay, which I mean doesn't happen obviously. Even if it were infinitely slippery, that's not the way fluid friction works. But we'll just pretend, right? So we get an idea here. It makes the math easier. It makes the model easier to use. And so we wanted to answer some questions about this, right? We came up with, if we're given the position function, we were able to calculate the velocity function and the acceleration function by differentiating, right? The really important thing to remember here when you're talking about rates, when we're applying calculus to something like physics, is what's the common parameter here? Well, it's t, right? They're all functions of t, which is, you may not fully appreciate that at first, but that's really huge. That allows us to link all of these kinematic quantities by specific moments in time, right? And I know this probably sounds a little cheesy, but the best way to think about this kind of thing, it really is to think about it like a video, right? Where you're indexing the frames in the video by the time that event happened, right? So we can pick a given frame in the video, and then we're going to kind of like try to toggle between these different views, the position view, the velocity view, and the acceleration view, where we're just going to calculate those quantities, right, for that video frame. That's a pretty good model. First thing we asked is how long does the bullet take to reach its highest point, and how high does it go, and what did we say, how did we approach that yesterday? What's significant about that frame in the movie when the bullet gets to its highest point?
It's not accelerating.
The velocity is zero, right? Acceleration's constant the whole time, but that's where the velocity is zero. And we did that math yesterday. We set the velocity equal to zero, and we solved, and we got 102 seconds, roughly, right? Give or take a tiny bit. So that's how long it takes to get up to the apex. Okay, and if we wanted to calculate how high it was, we just evaluated our position function, right? We're going to go back to our list of kinematic quantities right here, and we know that t is 102, and so we're going to choose that one. We want to know the value at that frame in the movie. Time equals 102. We want to know the value of y, so we just evaluate that function, right? Okay, good. So then next part was we want to know how long does the bullet take to reach the floor of Yosemite Valley below. Okay. Now keep in mind that this position function is relative to the floor of the valley, right? And we can prove that easily to ourselves by plugging in t equals 0. And what do we get if we plug in t equals 0? 1,000, right? So we know that we're starting 1,000 meters up off the valley floor, which is the rim of El Capitan. Okay, so that makes sense. So then if we want to know how long it takes the bullet to reach the floor of Yosemite Valley, how are we going to do that? We need to figure out which frame in the movie we're talking about, right? Mm-hmm. Okay. How are we going to do that?
Set your position equal to 0.
Set the position equal to 0, right? The floor of Yosemite Valley, what's significant about that, that's where y equals 0, right? Position equals 0. So we'll just set the position function equal to 0 and solve. And I think we did that, right?
Yeah.
And didn't we get, well, okay, we did it, but we never wrote down, so I might have to redo that. So that's something we'll do with technology, right? We'll use Desmos to do that. When we could use quadratic formula or something crazy like that, but we don't want to do that. No need. so there's the function, there's the equation we're solving, right? Our just really quick and easy numerical way to solve equations graphically is just graph the left side of the equation, graph the right side, and set them equal to 0, right? So in this case, we don't really even need to graph the right side. Y equals 0 is just the x-axis, right? So we'll graph y equals 1000 t minus 4.9 t squared plus 7000. And if we look for our zeros, we got to zoom out a little bit. There are my zeros. So in order to get a good picture for our notes here, let's see. What is the peak of this thing? How high does this go? Pretty high. What did we say it was, like 50,000 or something?
50,000.
50,000. Okay. So let's set our window then. We'll go, x is going to go, what is that? That's 205. So we'll go from, like, how about negative 10 to 220, and let's go by tens. See how I'm doing this?
Yeah.
Okay, and then on the y-axis, we'll go from like negative 5,000 to 55,000, whoops, in increments of, how about 5,000? Okay, so we get a pretty good picture then, right?
Yeah.
And we want to find the zeros. So our zeros are at negative 0.995 and positive 205.1, let's say, right, if we just rounded to the nearest 10. Okay, I'm going to get a picture. Okay, there we go. So there's our picture. We got the two values when we did this. We'll round to the nearest hundredth, how about? So we get negative, well, I guess that's just negative 1.00, isn't it? What was it, 205.08? Okay, so interpret that for me, please. Which one are we probably interested in?
The 205.
The 205.08. So that's how long it takes to go clear up in the air and fall back down into the valley floor.
Yeah.
Okay. All right. It wants to know. So this is the one we want for sale. Okay. How do we know how fast it's going?
Set that into the velocity.
There we go. So that's a frame in the movie, isn't it? Right? That's the frame when it hits the valley floor. And so all we'd have to do to find how fast it's going is plug that in to evaluate the velocity function there. And somebody real quick, what do we get if we do that? So V of 205.08 is what? Negative 1,009.8, and that's going to be meters per second, right? Okay, so it's always a good idea to kind of ask yourself, does that make sense? And so let's go back and look at the original problem, and let's just ask ourselves, is that a nonsense answer? And that really, I mean, you got to do that, because sometimes you get crazy answers that clearly are just way off. Is this one that makes sense? So we shot the bullet upward with a muzzle velocity of 1,000 meters per second. It hits the valley floor at 1,009 and change. Does that seem reasonable? Okay. Seems pretty reasonable. How fast, like when it comes zinging back by you, how fast would it be going, you think?
It would be as fast as you shot it up.
Ah, okay. Does it make sense? And it's, you know, I don't want to get too mired into physics here, but does it make sense that it would have, especially if you're in physics, does it make sense that when it comes back by you, the velocity would have to be negative 1,000,
Yes.
right? Okay? That's pretty cool. Could anybody give me just a short explanation for why that might be the case? What do you think, Nick?
Because it has the same acceleration going up and down, so
Okay.
the distance it travels from, like, the person to the peak, and from the peak back down to the person is the same.
Ah,
Either
okay.
way.
Okay, so the acceleration is the same the entire time, right? And so the acceleration that's slowing it down on the way up is gonna be what's speeding it up on the way down. Okay, that's I'll take that. Anybody else got a good physics argument for why that would be, why it would have to be that way?
Faster than that.
There's, to me, the most elegant way of explaining this, and I don't know if you guys have talked about all this stuff, but the most elegant way of just defending that immediately would be that the work done on the way down is the opposite of the work done on the way up, right? What's the only force acting? This is kind of, now I'm just talking to physics types in here, so you're in a physics class. What's the only force acting on the bullet the whole time it's in the air? Gravity. So the work done by gravity on the way up is gonna be positive or negative? Negative, right? Okay, what's that mean? If the work done by gravity is negative, then it's storing that as potential energy essentially, right? That's what's going on. So the energy is being converted from kinetic to potential on the way up. What's happening on the way down? The potential is being converted back to kinetic, and so the work done is just positive on the way down. But the magnitude of the works has to be the same, because the distance the bullet's traveling and the force acting on it are the same, right? Does that make sense? So that's a pretty elegant way to look at it. What's really interesting about this, though, this exhibits, so now I'm talking to everybody again. That work stuff is a little cryptic. This won't be. This is a really good example of kind of some higher symmetry that you see in math. Remember talking about symmetry, you know, back in geometry, you talked about rotational symmetry and line symmetry and all that stuff. And we were pretty limited there. We're talking about just simple geometric symmetry. But symmetry doesn't have to be that way. Symmetry can be with respect to lots of different things. And the more interesting symmetries you study in physics sometimes really aren't geometric symmetries. We have some really good symmetry going on here with respect to what? In this equation. Because, I mean, we got, and what I mean by this is, it's just, when you think about this kind of symmetry, it's just intuitively obvious that the velocity on the way down has to be negative 1,000 if it's 1,000 on the way up. Because this trip that the bullet takes from when you shoot the gun to when it passes by you is symmetric with respect to what? Okay, I'm going to hold that thought. Imagine now that we're going to film this thing with a video camera. We're going to film the bullet. It's got, I don't know, it's lit up so we can see the bullet the whole time, right? And we're filming it from a little ways away so we can see the entire flight of the bullet. If I film this with a camera, let's say, would you know, like if I film the way up and then I just reverse the film for the first half of the journey and splice that to the end, would you even know any difference?
No.
Would it look any different to you if I just reversed the trip up, or I let it run and you watched it actually fall down? You see what I'm saying there?
Yeah.
I'm saying it very well. But it would be imperceptible, right? The two would look exactly the same. So what's the symmetry with respect to that? Time. You get that? So there's a symmetry with respect to time here, right? And that's kind of the way, it's really bizarre, but physics, if you look at all the laws of the physics that you're studying in physics class, they are insensitive to the direction of the flow of time, which is really bizarre. They work just as well backwards as they do forwards, right? It's really strange, right? The only thing that, and so what that suggests is that time could run backwards just as easily as it runs forwards, right? Like there's some speculation that that, and this is, it looks like this is not gonna happen, but it's not completely ruled out yet. If you look at the universe, the expansion of the universe as a whole, what's the inevitable fate of the universe, right? We don't know for sure, but it looks pretty certainly as though the universe, because now we're seeing that there's this, the rate of expansion is actually accelerating, and I'll talk about that some other day. That's really interesting stuff. It deals with, it reminded me to talk about that, because that's, you guys would understand that, and it's really interesting. It has to do with the brightness of type 1a supernovas, and that's what originally showed us, like 15, 20 years ago, that the universe is not, it's not slowing down, it's speeding up. But anyway, so it looks like it's going to continue to expand, but we weren't sure of that for a long time, and we're still not absolutely certain. If there's enough mass in the universe, what could happen to the universe as it expands? It could gravitationally stop expanding and crunch back into a big crunch, right? Mathematically, at least. It's probably not going to do that. But if it did, the question physicists had for a long time was, if that happened, would time start running backwards? Because all the physics works equally well both ways, right? I mean, that was a serious question that physicists were asking. Would causality reverse, and would you experience everything backwards? Okay, not going to happen though, because it's what the one part of physics that is not insensitive to the direction of the time arrow is entropy. And so if you look at thermodynamics, that kind of saves the day. And so physics probably can't run backwards because of that. But all the laws that you study can flow in either direction, which is pretty interesting. Right? So you get this time symmetry, and kind of as you study math and physics, I asked you purposely to give me some explanations for why this thing comes back at the same velocity it left, same speed it left at, right? And there's a bunch of ways you can defend that, but the more elegant you can get, the more simpler your explanations become, right? So if you can just say, well, time is, I realize that there's time symmetry here, so, QED, it has to come back with the same. Then that's a pretty easy but solid explanation, right? Okay, I probably digressed enough there on that one. I think that stuff's kind of cool. Okay, so but I'm not quite done with this problem yet. There's one other little part of this. I want to know what is going on. The math gods never give us information that's totally worthless. So the math gods, when we ask them, by setting the position function equal to 0 in this situation, and this position function is predicated on all of these initial conditions, right? So you got to really focus on this for a second. This is really cool though. So if we take a situation where we're standing on top of a 1,000-meter cliff, and we shoot an object upward, a projectile upward with a muzzle velocity of 1,000 meters per second, that yields this exact position function. The position function is built from that initial information, right? Yeah. Okay, we did that, and then we set it equal to 0 and asked the physics gods, well, when does that happen? And they told us. They told us that it happens at two places, at -1 second and at positive 205.08 seconds. Well, this is the one that was more meaningful to us in the context of the problem we were doing. But this one can't totally be ignored. What are they trying to tell us? What are those physics gods trying to tell us with
The velocity at those points opposite.
that solution right there? What do you think?
Well, that's like because you're 1,000 meters up, if you shoot it, if it went like straight down, it's 1,000 meters per second would be take 1 second.
Okay, so there's one way to kind of, that's a useful piece of information that comes out of this. You want to add anything to that? What do you think?
I was gonna say, if the bullet were to somehow emerge just from the ground randomly, then it would take 1 second to reach the point that it was actually shot at, and it would
Okay.
take 1 second to reach that velocity.
Okay, yeah. So the physics gods, they're very mathematical. They have no idea what a rifle is. They have no idea what gunpowder is. All they know is the initial condition that you gave them was that the bullet is going to go by the edge of the cliff at 1,000 meters per second. It's irrelevant to them that we're shooting a rifle, and so it's leaving the gun, and it started from. They don't care, right? All they care about is when it leaves the end of that metal tube, it's going 1,000 meters per second, and we're this high off the valley floor, right? So from their perspective, that could just as easily have been holding out a metal pipe and a bullet comes whizzing up from the floor and passes through the pipe and emerges from the end of the pipe with 1,000 meters per second of velocity, right? If it did that, if that's what really happened, how much earlier would it have left the valley floor? That much earlier. Can you tell me roughly what its velocity would have been when it emerged from the valley floor suddenly? About 109, or 1,009 meters per second, right? Because it had to go by the cliff at 1,000. So it really did tell us something. It just wasn't, you got to kind of be careful, because they, like I say, those physics guys, they don't really understand all the intricacies of the problems. They don't know what a rifle is, but, so they're giving you information that is valid, it's just not contextually applicable to our situation, right? Okay, make sense? Okay. So what about something like this? Here's another issue that comes up, I just want to make sure you're okay dealing with it. It's not hard, but I want to make sure you understand this. So another mathematical model. The body mass of certain type of sheep can be estimated by this model, where M is measured in kilograms and T is the number of days since May 25th. Okay? And it's giving us this model that's predicting the body mass as a function of time. So part A, look at part A here for a second. It says find the average rate of change, and that's what I want to make sure we understand. The average rate of change of the mass between 101 and 113 days. Okay. What's an average rate of change?
The rate of change, one plus the rate of change, the other. Difference between.
Okay, so is it, so the suggestion is like the derivative there and the derivative there and averaging them or something? Is that what you're saying?
I don't think so.
Okay, I don't think so either.
The second derivative, not the first.
Okay, you guys are trying to make this into a calculus thing. Is it a calculus thing?
No.
It's not a calculus thing, is it?
You just.
An average rate of change is always just what? It's going to be, so the average rate of change of the body mass index, whatever we're going to call this, the body mass, is just going to be the change in M over the change in T, right? It's just a rise over a run. More importantly, it's the slope of the secant line connecting those 2 points, right? If I were to, like, let's just graph this thing and see. I want you to see this visually. And this, it's not like this is a big, mysterious point I'm making, but it's a really important one to be able to distinguish these two things.
You go to the aggregate, and that's the consistent velocity of sheep.
Okay, so here's our, let's make a new function, m of t
You need to get
equals 2, I'm gonna have to probably change my window, but that's okay. Plus okay, so there's my function. I got the graph settings all messed up, don't I? Let's see here. Okay, and if I zoom out a little bit, so there's my, you can see our function right there, right? And we want to go from days, what was it again, do you remember? I don't remember. 101 to 113, okay. So then look what we can do here on this. This is, you kind of learning some Desmos stuff here. So I could calculate what is M of 101 it was?
Yeah.
So that's, the output is like 47.7. M of, what was the other one?
113.
132?
113.
113. Okay, there's the other one. Now, if I want to, I can see these points on here too. This is kind of cool. Watch this little trick on Desmos. I can make some ordered pairs. I could do something like 101, comma M of 101, and it gives me a point. And if I put a comma there, I can put multiple points. Okay? And so that's the part we want to kind of focus on right there, right? all I'm looking for is the slope of the secant line connecting those points. That's gonna give me my average rate of change. Everybody agree?
Yeah.
Okay? Well, what is the slope of the secant line? That's just the difference quotient, right? If we go back to when we first studied, derivatives, and we were trying to come up with a way of calculating derivatives, what did we do? We took a limit of the difference quotient. That's all we really did, right? We took the limit of the slope of a secant line to get the slope of a tangent line. Okay, so in this case, the slope of the secant line is just going to be the change in y. Well, it's not y in this case, it's m, right? Over the change in x, but it's not x in this case, it's t. Change in the output over change in the input. Which is going to be whatever we get, what's the change in m? Well, that's going to be m of 113 minus m of 101 divided by the change in t is just 113 minus 101. And that's going to give us some answer, right? And we can plug it in and see, but I'm not going to bother. It's going to give us some value, isn't it? Right?
That's good.
Okay, we're going to get some average rate of change based on our function. Okay, now how's that different from part B? Find the instantaneous rate of change at day 101.
Isn't that just 10?
So what's instantaneous rate of change now? What's that connecting us to? Derivative, right? That is the slope of a tangent line. We want to know, in that case, we want to know what it, at that exact moment, if at day 101, how fast is the mass changing, right? So that is going to be a calculus issue, right? That is the slope of the tangent at t equals 101. Well, that's just derivative, right? So that would just be m prime of 101. You agree? And we don't have to, you can do that. We could differentiate that, it's just a polynomial, right? And then plug in 101, okay? Do you want me to do that one, or are you okay with that?
I think we're good.
Okay. Is it weird to do, like, what would that last term be if I differentiated that?
0.002.
Okay, everybody see that? We're just gonna differentiate these term by term using the power rule. So I bring the exponent down, I get negative 0.002 times t to the 1, for example, for that term. Derivative of 26.7 is 0. What's the derivative of 0.3t? 0.3, okay. Okay. This was kind of a cool one.
Sweet. Sweet.
So we've got this law here that tells us if you're looking at, and this is just laminar flow. You guys probably haven't talked about any fluid stuff in physics here, right? How do you say his name? So, I don't know. I'd say probably.
We're saying Po.
Po.
French word. It's French. Po.
Oh, poise. Poisson, I suppose.
Poisson.
Poisson is
Not
sure.
Someone search it.
Are we out in 1 minute?
No, we got
No, we
11.
got-
Okay, good. So this is kind of cool. So here's another interesting model where we can use calculus to help us out, help us understand this a little bit. It tells us that the velocity of blood is given by this model, where capital R is the radius of the blood vessel that we're looking at, and little r is the distance from the center of the blood vessel, the radial distance from the center of the blood vessel. So what this is depending on is what's called laminar flow. And just quick defense of that, or just an explanation of what laminar flow is. It's a good model for fluid flow, right? And this is, if you're not in physics especially, this is something that's kind of just nice to think about fluid flow in this way. If you've got, what laminar flow says is that you can think about the flow of fluid through a pipe or something. Let's take a nice simple pipe, so it's got a round profile, or cut through the cross section. You could think of the water as flowing in little layers, like concentric layers, like when you recycle cans and you put the big ones on the outside, and then you can nest them like that. So if you look from the end, you'd see concentric circles, right? Those would be the layers of water. You get these concentric little shells of water flowing through the blood vessel. where, or flowing through the pipe, where would you expect water to flow the fastest?
In the center,
In the middle, how come? And where would it be the slowest?
on the outside.
On the outside, okay, so why would it be slower on the outside? Because it's rubbing against the outside of the pipe, right? It's gonna have some interaction with the outside of the pipe. In the middle, it's gonna be furthest from that. So the slowest layer would be that layer of water right next to the edge of the pipe. The layer next to that would be a little bit faster, but it's gonna interact with the slow layer of water, right? And as you go further towards the middle, they gradually are just gonna speed up, and you get that one little, like the little pencil lead in the middle, that's gonna be going the fastest, right? So that's what laminar flow is. And so we're kind of talking about the flow as being organized in that way. So what would we mean here then by something like the VDR? Because that might, if you were studying, let's just say that you end up studying biophysics or something, right? So you're developing equipment to try to, diagnostic equipment that's gonna measure blood flow in some way. You would study this in depth, and this might be a really interesting quantity to you if that was what your career was focused on, was studying the flow of blood and blood vessels. And it could be, you never know. What does that mean? The VDR. By R, it's the little r.
Relations of velocity to the radius of the blood flow? No,
The
actually, no,
distance.
It's the distance.
How far is it traveling at what velocity?
Okay, you'd want to start your answer, no matter what, before you even think about this, you know it's going to be the rate of change of something.
The blood flow,
The rate of change of
velocity.
velocity with respect to
The radius.
radius, so the distance from the center, right? So what you're looking at here is you're looking at how fast is the velocity of the blood changing as you move from the center of that blood vessel, right? As you move radially from the center towards the edge maybe, or something like that, or from the edge towards the center, right? And that might be interesting to know. You might want to know, where are you going to make your measurements of blood flow or something. You want to know, well, probably maybe where is this changing the fastest and where is it changing the least, right? You might want to come up with some kind of a function. Does that make sense? Okay. Sometimes it's really hard to get at the concept of these rates. What's that mean? Well, okay. Yeah, I think that's all I have. Questions? All right. You got an assignment. I'll push the dates off, and I guess I need a little feedback on this one.